Welcome to the web tutorial VERfutures Calculation. This web tutorial was especially designed for project developers and will explain how to calculate the amount of VERfutures. This presentation consists of various chapters which include definition of VERfutures, how to determine the eligible area, and how to determine their volume, conversion of cubic meters of wood to tons of CO2, and how to quantify the CO2 stored in your forest. Therefore, we will define the parameters future CO2 fixation, project emissions, baseline, and leakage. Then we will learn how to fill in the different templates, and at the end of the presentation, we will go together to the website to learn how the information must be submitted. You can also go to another chapter by clicking the menu button at the bottom of the screen. As this video uses the simplified wording in comparison to the CarbonFix Standard, we will refer you throughout the video to the respective documents for more detailed information. So let's start with the first chapter, definition of VERfutures. Certificates generated by the CFS are called VERfutures, which stands for Voluntary Emission Reduction. The additional word future emphasizes that CO2 will eventually be stored in the full-grown trees. The unit of one VERfuture is 1 metric ton of CO2 equivalent. The formula to calculate the total amount of VERfutures is the eligible planting area times the future CO2 fixation from which the project emissions, baseline, and the leakage are deducted. Let's have a closer look on the different parameters of this formula. Within our formula, we will firstly define our eligible planting area. To better illustrate the different types of areas, the following polygon will be considered our example project area with the total size of 800 hectares. On parts of this area, no VERfutures can be generated as this land does not meet the criteria of the CarbonFix Standard. VERfutures certificates can only be generated on areas which are not wetland, which are not officially protected, and where there has not been an existing forest for the last 10 years. In our example case, all these criteria are met by the remaining area, which is therefore defined as our eligible planting area. As our example project area is 800 hectares, we now have a remaining 500 hectares of eligible planting area. We've now calculated the size of the total eligible area, though, for the parameter in the formula, we will need to know the size of the management units within this area. This will be explained at a later stage of this web tutorial. Let's move together to our next chapter called carbon pools. Carbon pools are biological units that store CO2. There are different carbon pools which are used in our parameters, including future CO2 fixation, baseline, and leakage. Overall, we categorize the carbon pools into woody and non-woody biomass. There are other carbon pools, such as dead biomass, soil, or wood products. Due to the reasons of practicability, these pools are not included in the CarbonFix Standard. To learn more about the scientific background why these carbon pools must not be considered, please read through the CarbonFix methodology. To be able to calculate these parameters, future CO2 fixation, baseline, and leakage, it is also important to know how to convert forestry units such as cubic meters of wood or tons of dry biomass into the climatic unit of tons of CO2. To understand this better, the following graphs of the CarbonFix Standard will assist us. They can also be found in the CarbonFix Standard. We recognize in the middle of these graphs are two carbon pools, woody and non-woody biomass, which further split into above ground and below ground. Along the lines of the graphs, the different factors to convert the carbon pools into metric tons of CO2 are explained. Let's follow the line of the woody above ground biomass as an example. We see on the far left that this carbon pool is based on the stem volume of a forest, which is normally determined by forest inventories. As the word volume already tells us, the unit of this parameter is normally in cubic meters. if we are now multiplying the stem volume times the biomass expansion factor, often abbreviated BEF, we derive the total wood volume. Multiplying the wood volume of a forest times the wood density, we get to the woody biomass, which is now the unit of TDM, which stands for tons of dry matter. We now have to multiply this by the carbon fraction of the wood, which is fixed to 50% or 0.5, N times 3.666, to derive the amount of carbon dioxide. As mentioned before, the output of this calculation is the above ground woody biomass with the unit of tons of CO2. Translating the graph into a regular formula, it would look the following. Above ground woody biomass equals to the stem volume times biomass expansion factor times wood density times carbon fraction times C CO2 factor. Considering all these different values which influence the calculated amount of CO2, it is most important to follow the so-called conservative approach, which is explained in the document, the CarbonFix Criteria and Methodology. Let's determine together our first parameter, future CO2 fixation. For this value, only the carbon pool woody biomass will be considered. In other words, the above ground trees, together with their below ground roots, determine the future CO2 fixation. The method on how to calculate the amount of CO2 stored in your trees depends on the silvicultural system you are applying. The CarbonFix Standard distinguishes hereby between two systems, selective harvesting and rotation forestry. In the case of selective harvesting, your future CO2 fixation is determined by the amount of CO2 stored when the forest reaches its equilibrium. This normally depends on the maturation age of your trees and the amount of wood you will sustainably harvest. Using this type of silvicultural system, your future CO2 fixation normally ranges between 500 to 800 tons of CO2 per hectare. In the case of rotation forestry, your future CO2 fixation is determined by the mean amount of CO2 stored within the first rotation period. Hereby, your future CO2 fixation is normally somewhere between 250 to 400 tons of CO2 per hectare. Going back to our example project area, we see that, step by step, the eligible area is being planted. Therefore, so-called management units are installed, which are areas that contain trees with similar growth patterns. These patterns mainly depend on variety of tree species, the soil properties, and of course, the year of planting. For each of these management units, a forest growth model must be established to determine the future CO2 fixation. We will shortly go into the details of such growth models. Furthermore, we now see that our example management unit 1, with the size of 100 hectares, was entirely placed on land which is eligible. Consequently, these 100 hectares represent our first parameter, eligible planting area. As explained before, we now first of all have to set an accurate growth model for the conditions on management unit 1, which you will have to research in the literature. This describes in detail the growth of the trees on our first management unit. As you can see, we have planted a forest where trees will be used selectively. In our example case, the growth model predicts that the forest will reach its equilibrium at 324 cubic meters of wood per hectare, which converts to 490 tons of CO2 per hectare when calculated with the conservative approach. After we have now determined the future CO2 fixation, we can move on to our next parameter called project emissions. Project emissions are amongst others caused by machines, flight, and the administration of the project. To account for these emissions, a flat rate of 0.5% from the future CO2 fixation must be deducted. Additional to this, projects that are using fertilizers must deduct 0.4 tons of CO2 per kilogram of nitrogen used. In our example case, we do not use any fertilizer, but still have to account for the regular project emissions. Therefore, we have to deduct 0.5% times 490, so 2.45 tons of CO2 per hectare. As no digits are possible after the decimal point, With the CarbonFix system, it will be rounded off to 3 tons of CO2 per hectare. After we have now defined our project emissions, let's move forward to our next parameter, the baseline. The baseline is determined by the amount of CO2 which is stored in our eligible planting area during the time of the project start. In contrast to the future CO2 fixation, which is based on the carbon pool woody biomass, we now have to consider for the baseline also the carbon pool non-woody biomass. To show you how to determine this parameter, let's go back to our example case. In our example, the entire eligible planting area consists of 300 hectares of grassland and 200 hectares of land where shrubs grow. According to the inventories which were executed on these areas, the grassland stores on average 10 tons of CO2 per hectare, and the shrubland on average 20 tons of CO2 per hectare, which is the sum of both above and below ground. If you need guidance on how to execute such inventories, please refer to the Inventory Guideline, which is provided you by CarbonFix within the login area, under the menu point, Templates and Guidelines. Overall, we now have 300 times 10, which equals 3,000 tons of CO2 stored on our area covered with grass, and 200 times 20, which equals 4,000 tons of CO2 on our total eligible area with shrubs. Summarizing this, we derive a total baseline of 7,000 tons of CO2. Per hectare of eligible area, which was in our case 500 hectares, this gives us 14 tons of CO2 per hectare. In case your project burns this baseline biomass, to prepare the planting area, an additional 10% of the baseline must be added. This is due to greenhouse gas emissions other than CO2 which occur during the burning process. In our example, this is not the case. Let's move on to our next parameter, leakage. The leakage parameter is determined based on activities which are shifting from inside to the outside of the project area. For this parameter, the entire project area must be considered. For the leakage, only the carbon pool woody above ground must be considered. There are 6 different types of leakages defined. They are caused by the displacement of the following activities: the use of fuel wood, the production of charcoal, the harvesting of timber, agricultural farming, the relocation of houses or communities, and the displacement of livestock activities. For the calculation, we cluster these types into 2 categories. Human shift, which includes activities where people move to other places in order to continue their activities, and livestock shift, whereby animals are shifting to other grazing land. Let's go together through some of the calculative examples to clarify how the leakage emissions will be determined. In our example case, people used to collect fuel wood on the project